In this video, Dr. David Francis provided the description of lattice design, types, the properties, as well as the ANOVA table. The descriptions including some advantages and disadvantages of the design and when lattice designs are commonly used. The statistical model is also discussed.
Lattice designs are an incomplete set of treatments in each block. They are ideal for treatments with a large number of treatments. So in our case, treatments is often lines or genotypes. The advantages are that they increase the homogeneity within a block, increase precision. The disadvantages are that there are a fixed number of treatments and replications that have to be there for the design to be resolvable. The analysis is fairly complex, especially if you're going to do it by hand. And there's also unequal precision in the treatment comparisons. And this is a different way of phrasing what our blocks don't have all treatments, yet we're adjusting for the block effect. So if one block happens to have high yielding or low yielding lines by chance alone, that's going to be reflected in the adjustment. Okay? So lattice designs tend to be used in large experiments. You can reduce the number of treatments in a block. We often have a large number of genotypes, and so we may not be able to fit them all in a block, especially if that block actually means something in terms of an environmental parameter. Often if you're doing, say, insect vectored virus work, you've got a cage that you can put a certain number of plants into with the insects, and there's a limit to how many you can put in a cage, so you simply can't get all your treatments in. So the incomplete design or the lattice design becomes an appropriate way to make that work logistically, based on space constraints. Lattice designs are a well-known type of resolvable incomplete block design. This slide is demonstrating what a lattice design looks like. So we have 2 reps, and each rep has 3 blocks. T is our number of treatments. K is the number of units per block, in other words, the block size. B is the total number of blocks in the experiment across both reps. R is the replicates of each treatment. And S is the number of blocks in each complete replication. The key is that S times R is equal to B. Next, we have the different kinds of lattice designs. So in the square lattice, T is equal to K squared, and S is equal to K. In a rectangular lattice, T is equal to S times S minus 1, and K is equal to S minus 1. You can see the relationship between the square and the rectangular. Alpha lattices have this property of T is equal to S times K. T is the total number of treatments, S is the number of blocks within a rep, so the block number, and K is the number of plots within a block or the block size. So this is the properties of the alpha lattice. So we can write this out as a linear model. So we have our treatment effect, so we have the average, we have a treatment effect, the replicate effect, the block within replicate, and our error. The alpha lattice is resolvable as long as K is a factor of T, works for any combination of T is equal to S times K, and the number of treatments is fixed. There are different types of designs depending on the number of replicates and the relationship between K and S. And so you'll hear people talk about a design 1 or a design 2, etc. So we can lay out the analysis of variance just as you would for a randomized complete block design. The key here is that there is an adjusted sums of squares for treatments, sums of squares and mean squares, as well as for blocks. And it's this adjustment that you have to make in order to get out your adjusted means for treatments. And you can run an ANOVA and then make these adjustments by hand.